Rightio, so now we're up to talking about latent heat. So we've talked about specific heat capacity, how that is the amount of energy to increase the temperature of 1 gram of substance by 1 degree C. Now we're going to talk about latent heat, and this is a sort of conceptually something that's a little bit strange. So let's just dive in and see what we're talking about in terms of definitions. So we said that water has a high latent heat value when we talked about its properties, okay? And this is, I guess, latent heat's the easiest way to say it. It's hidden heat. It's the energy needed to change the state of a substance at its boiling point or melting point, okay? And we know that there's a gradual increase in temperature needed for any amount of substance. If you think about it, when you start to boil water, not all the water starts to boil at the same time. You don't have an instantaneous phase change. Some water has energy high enough to start turning into a gas before other water does. And this tends to follow what we call a Maxwell-Boltzmann distribution. So you have a graph that's sort of like this. Okay, so under here is the proportion or number of molecules. Okay, and then we have the amount, this would be our energy. Okay, at any point in time, there are some molecules that have a low energy, and there are some molecules that have a high energy. And then we would have the average kinetic energy in the system, which is the energy range under which most molecules would be in. Okay, much the same as you have a grade distribution in any class. You have some people who have lower grades, some people who have higher, and then you have the bulk of the class will be around the middle, you know, C's and D's. Okay, same for molecules in a substance. Okay, some have high energy, some have low energy. So as you heat it, these molecules are going to undergo the phase change sooner, so they're going to head off into the gas, but you're going to have to need to keep adding energy to push these up into the phase change. Okay, so when we go from water to gas, we need to absorb a latent heat amount, okay, the energy required for the phase change. Okay, and then we have the same thing when we go from solid to liquid, and then the latent heat is released when we go from a higher energy to a lower energy. Okay, so if we think about it, phase changes from a lower energy state to a higher energy state are going to be endothermic. Phase changes from a high energy state to a low energy state are going to be exothermic. And the endothermic is going to be the amount of energy that we need to put in is our latent heat value. So the latent heat of fusion, and this is a definition we must know in our definitions that we're going to write down. Latent heat of fusion is the amount of energy required to change a fixed amount of substance or water from solid to a liquid at 0 degrees C. Okay, so this would be the definition for the latent heat of fusion of water. This is because water's water's melting point is at 0 degrees C. So it's the amount of energy required to change the state of a substance at its boiling point or melting point. Fusion is talking about the solid-liquid interface. Okay, so fusion, fusing into the solid. So the amount of energy required to change a fixed amount of water from solid to a liquid at 0 degrees C. Latent heat of evaporation, or latent heat of vaporization as it's sometimes called, is the amount of energy required to change a fixed amount of water from a liquid to a gas at 100 degrees C. 100 degrees C being the defined boiling point of water. Okay, and again, the fixed amount. So if we have a look at this, okay, this is what a typical heating curve looks like. You may remember this from doing ice to steam in year 7, where you had to take a beaker of ice and then heat it up over a Bunsen burner and measure the temperature as it changed. And if you had actually done it for long enough, what you would have realized, if it had started boiling, would be it would start to plateau because you were at this part of the graph here. But what this graph is saying is that at this point, the solid heats up, okay, until it reaches This is the melting point of the substance. Once it reaches the melting point, what you have over this flat region is during the phase change. So this is when it is a mixture of solid and liquid. The temperature does not change while there is a mixture of two phases. Once it is all liquid, so now it is all liquid at this point, and remembering time is essentially mean we're still putting in energy over time, okay? Still putting in energy. So we're putting in energy, but the temperature is not changing. Once it is all liquid, the temperature will start to rise again, okay? Until we get to the gas-liquid interface, where the temperature will stop rising while it is boiling. Okay, so this is while it is boiling. This will be while it is melting. Okay, and then it will start to rise. It is this period here, while energy is still being put in, that we're talking about when we talk about latent heat. Okay, it is all the energy that is going into the system during that phase change as we talk about latent heat. So water's latent heat is actually quite high, okay? Its heat of vaporization is important to maintaining life on the planet because it means that the water's temperature stays fairly consistent, and we see that in our oceans. Our oceans' temperatures don't fluctuate a lot, which gives rise to a huge ecosystem of environments of plants and animals that can live in it. It also helps to regulate the temperature on our planet in terms of water in our atmosphere. Okay, this also allows water to act as a cooling system for living organisms through temperature regulation, sweat, and things like that to help us cool. And because it has a high latent heat of vaporization, it doesn't evaporate as quickly as other liquids would for the same amount of energy coming down from the sun and things like that. So if we have a look, latent heat of fusion, so this is, remember, the solid-liquid interface. So this is at the melting point of 0 degrees, okay, for water, is 6 kilojoules per mole. So it takes 6 kilojoules per mole, okay, to make 1 mole of water change state from solid to liquid. But if we look at the latent heat of vaporization, it's 44 kilojoules per mole of water, remembering that 1 mole of water is equal to 18 grams. So that's 44 kilojoules for every 18 grams of water, which is a huge amount of energy. Okay, so we can incorporate this, much like with specific heat capacity, we can incorporate this into a number of calculations, where Q, again, is our heat energy, okay, in joules. N is now the number of mole of substance, because we said that it was going to be for a specific amount, and specific amount for chemists is always mole. And then L is what we use for latent heat. Okay, so this could be latent heat of vaporization, which would be 44. Okay, so latent heat of vaporization is 44 kilojoules per mole. Okay, or it could be latent heat of fusion, which was our 6 kilojoules per mole. Okay, so you need to check the phase of what you're talking about. Are you at the liquid to gas or solid to liquid phase, so that you use the right latent heat value. This is the worked example from your textbook, okay, where it says calculate the heat energy required to evaporate a given mass of water at its boiling temperature. Okay, so in kilojoules, 200 grams of water. Remembering now we're not using mass because we only use mass for Q equals MC delta T. We're at the boiling point, so this is going to be evaporation. Okay, 200 grams, we're going to need to convert that into mole. Okay, and then we're going to get kilojoules. So we're going to work out the number of mole. 200 divided by 18, which is molar mass of water, to give me 11.1 mole. Then we're going to use our latent heat of vaporization, which is 44 kilojoules per mole. This is already in kilojoules, so I know I'm in the right unit for my energy. So I'm simply going to take the number of mole and multiply by the latent heat of vaporization to get 488 kilojoules. Try this one yourself, okay? And just to practice this, remembering we are it's telling us evaporate. Okay, so you're going to need to work out the number of mole here, and again we're using latent heat of vaporization, and then just substitute in to this formula. Okay, so that's all we're doing with latent heat. Okay, just using that latent heat. Q is equal to N times L, and remember we have Q is equal to MC delta T. Remember, this is joules for our energy. L is given in kilojoules per mole. Okay, so you need to pay close attention to those units. Have a quick summary of this, remembering to put down the definitions of your latent heat of vaporization and latent heat of fusion, your new formula, making note of the units. Refer to your worked examples as you try these questions from your textbook, and I'll see you in class.